we're going to talk about fronts. And when it comes to fronts, here is where, generally speaking, the weather gets really interesting. Now, we've seen in the section on air masses that specific types of air masses can have different types of weather. Now, that said, when two air masses move along and then they suddenly collide, that's when things get really interesting, to say the least, weather-wise. You can see here a number of different fronts, and we're going to talk about all of these as this section goes on. Now, yes, I know you were looking at the timer and you were like, this is another big one. Well, that's because we're dealing with a huge topic, air masses, and then where they meet, which typically are many, many, many miles across. So, let's get into it then. Let's start out with a definition of fronts. That being the case, a front is the transition zone between two air masses. Now, in order for a front to exist, we need to have a huge difference in terms of temperature between those two air masses. If the temperature variation isn't that great between the two of them, then we won't generally have a front form. Now, fronts can be thought of as the battle zone between those two air masses. It's where they're kind of duking it out and trying to see who's going to become superior. Now, that said, as a meteorologist and as a pilot, that fighting it out produces all sorts of interesting things. When it comes to fronts, when they're going by, I shouldn't really say when they're going by, often when they're approaching if it's a warm front, but definitely when they're going by, and sometimes after they've passed, in the case of a cold front, you are going to see many, many changes. For instance, we said temperature, right? Temperature is going to change. Well, that's one. But other things will change as well. We can see the winds will change, the moisture content, because we've got two different air masses again, and humidity. Now, the exact weather that happens at a front is quite complicated, and it can be different every single time. The reason for this is there's a number of factors that will help determine the weather as a front goes by. Things like the stability and moisture content of the warm air mass. Remember, two air masses colliding, a warm air mass, typically a colder air mass as well, much colder, not always, but, relatively speaking, a colder air mass. The warm air mass frequently determines the amount of precipitation that we end up with. The stability of that air mass will do the same thing. It will determine how much precipitation we're going to get and how violent it is. It will also depend on the speed of the front. Now, notice when we say speed of the front as determined by the cold air mass, the cold air mass determines a lot for us as well. And we'll see that in just a few moments as we go over to the whiteboard. And then finally, we have the slope of a front. When we have fronts, you're going to discover that they have various slopes to them. The more steep the slope is, generally, the more interesting the weather will be. Now, before I go any further, what I want to do is actually simplify things as much as I can, and we're going to do that over at the whiteboard. And then we'll start to introduce more and more complicated ideas as we work through this whiteboard section and as we continue to look at fronts. So let's go over to the whiteboard. So what I want you to start out doing is imagining those air masses as those blobs of air that they are. And you know what? To represent one of these blobs of air and how air masses interact with one another, let's imagine that we had a jar. So there we go. We've got a nice little jar here. And in this jar, what we're going to do is we're going to put two substances of different densities. You're often doing this when you're checking the fuel in your aircraft. But let's say that I filled this jar up, maybe with some oil. So there we go. we've got this jar partially filled with oil here. And now what we're going to do is the oil is very light, so it's low density. We can almost think of the oil as being warm air. Now, if I took a cup of water and I poured a little bit of water into this jar of oil, of course what I'm going to find is that the water is going to pool up in a little bubble at the bottom, something like that. So what we could say is we could say the water, being more dense, is going to sink to the bottom. That's going to represent our cold air mass. So what happens is, in the atmosphere, remember the cold air being less dense, it tends to sink a little bit, and it gets surrounded by this warm air. What the cold air can then do is it can then start to move around within that warm air. So when we talk about fronts, it's the cold air mass, that little bubble that's moving around, that determines the name of the fronts and determines the motion of the fronts as well. So let's imagine this bubble, this warm air, and now what I want you to do is think for just a moment of this in relation to the Earth. Now we're going to look at the edge of the Earth, and we're then going to imagine a nice zone where we've got an Earth with a constant and consistent warm air mass. Now this is idealized again, and it's simplified. What we're going to have is, let's say that maybe this is something like maybe maritime tropical air somewhere out there. If we have some sort of a process that could then develop something like a bubble of, say, continental Arctic, and I'm just going to adjust this little bubble just a little bit. I'll just redraw this bubble. So if we had a bubble of cold air, let's say something like this. There we go. That's better for what I want to show you in a few moments. So if we had this bubble of continental Arctic air, we now know that this bubble is now free to start to move. And in this case, we're going to imagine this particular bubble is moving in this direction. Now, what I want you to notice is look at the front of this bubble. You can see how it's kind of like a teardrop because it's moving in this direction, and friction from the Earth is going to start to cause it to kind of move and bend underneath itself. There's the motion of the bubble like that. Notice how the back end is fairly flat. Now, we'll come back to those ideas in just a little bit. What I next want to do, I'm going to erase this here, our little jar of oil and water. And then I'm actually going to redraw this just a little bit higher for us so that I can start to introduce a few other objects. So we'll draw that edge of the Earth's surface again. I'm going to redraw this idealized warm air. And then let's draw our little bubble of cold air. Okay, and as we said, we'll imagine that it's moving in that direction. Now, let's next take a look at the top-down view. So this next view is going to be imagining that I'm a bird and I'm looking straight down at what is happening to this air mass. So if we were to draw kind of like a square around this on the surface of the Earth, that square would have the blob right in the middle. So let's draw this cold air mass right in the middle. Now, remember, what's happening is overall, this cold air mass is moving in that direction. And just for the sake of argument, I'm going to say that it's continental Arctic. And remember, the source region for any air mass is always going to be a high pressure region, right? So we need to remember that out over here, all around this bubble of cold air, I've got, of course, warm air surrounding it. Now, as this bubble moves, this cold air is going to advance into the warm air. So this warm air, or this cold air advancing into the warm air, will be given a series of symbols on a weather map. And it will look something like that, kind of like a barbed porcupine. So there we go. This is our cold front. The cold front is where the cold air is advancing into the warm air. Now, on this back side here, well, of course, the cold air is retreating. So, where the cold air is retreating, a meteorologist would actually draw a series of warm-looking half semicircles. So, nice bright red, like that. This here is what we would call our warm front. Now, on the sides here, the air really isn't retreating, nor is it advancing. So in that case, what the meteorologist will do is they will do something like this. This zone here is stationary. This zone here is stationary as well. So the meteorologist will then draw it on the map like this. You can see how it alternates, the warm barbs and the the cold barbs and then the warm little handles. So this would be the stationary zone. Now, what I want to do next is I next want to concentrate particularly on this one here. So we're going to imagine taking another cutout. So here's my inset cutout. So here's my cold front, as I mentioned. And then right here, of course, this zone here, if I was to cut this out, we would call this my warm front. Now, I want to specifically take a look here right now at the cold front. Okay. So this zone here is what we're going to zoom in on, and I'm going to zoom in on that up over here. Okay, so let's do that. Let's draw our zoom in area again. So I'll just create our little box here. Now what we would see is this, if we were able to zoom in. Of course, I've got my warm air over here. If I took my front and I drew it like a meteorologist will, it would look something like that. So there's my actual frontal zone itself. And they would draw their little barbs in on it like that to say, hey, this is the cold front, and that is the direction that it is moving. Now, of course, back here, we are going to have the cold air. But fronts are never, ever instantaneous. I don't go right away from warm air to cold air. I actually have right in here with a cold front what we call the mixing zone, or sometimes also called as well the frontal zone. Warm air does the same. Notice with cold fronts, the mixing zone is always behind the cold front. But here's something interesting with warm fronts. When we look at warm fronts later on and we zoom in on them and look at them three-dimensionally, you're going to see that the mixing zone actually is ahead of a warm front. You might be like, well, why is that? Okay, it doesn't make sense right now, but in a little while, hopefully it will. Remember, fronts always have mixing zones. Now, I think what I'm going to do next is I'm now going to go back to the presentation for just a moment. And yeah, let's do that. Because what I want you to think about is Rossby waves. And you might be like, why Rossby waves? All right, let's go take a bit of a review here at the presentation now. All right, so I want you to think back to the presentation on winds. Hopefully you've already watched the presentation on winds. And you might remember towards the end of that presentation, we had a weather chart like this one. Haha. Now, this particular weather chart is for the highest altitudes of the Earth. But it still gives us a really good sense as to where the air masses are going and what they're doing. Remember, we've got the pole up here, and then what we have is all of the colder air kind of working its way down towards the south. Warm air coming up from this direction. So what we end up with is these series of very cold pools of air. So there's one there, and then here's one here. There's another one drawn out here, and then another one here, and then another one here, and there's possibly another one right there, although it's hard to tell because that doesn't go all the way over and across into Russia. So think of these starfish patterns. Now what I'm going to do next is I'm actually going to show this in 3 dimensions on the whiteboard. Remember these and think about what we've been drawing on the whiteboard so far in terms of these blobs. You can think of these as big blobs moving southward. All right, let's go back over to the whiteboard then. So if I was to take a look at one of these Rossby waves, so remember, cold air sits permanently pretty much over the top of our poles. So I think it's safe for me to erase all of this now then. I don't need any of this for this part of the discussion. Keep this in mind. If you've got a memory that's photographic, keep that in mind for later on. And let's start to think about, again, the surface of the Earth, looking at it from the side. So here's the surface of the Earth. And then in this case, what I'm going to do, actually I'm going to need a little bit more room. So what I'm going to do is actually put this a little bit higher. I think I'll have enough room if I go like, yeah, this should do the trick. Okay, so we're now going to draw in, there's the North Pole right there. So if I was to think of this cold air as sitting upon the surface of the Earth, remember, it would overrun the pole like this cold air, and kind of move in like that, and then we end up with a pool of cold air like this, then we'd end up with a pool of cold air like that, and then kind of end up again with that happening like that. So we can give this a little bit of thickness, and imagine this, something along those lines. So if I was to draw in my Rossby waves, I'd be like, okay, so there's one axis of a wave right there. There's another axis of a wave right there. There's another axis of a wave right there. Another axis of a wave right there. And then we've got another one back here and another one back there. All right, so again, remember, this here is very cold air. And then over here, of course, we have warm air, we have warm air, and then yes, we would have warm air here as well. Now, out over here, we've got a high pressure area. And this warm air is kind of filtering its way in that direction. Now, this high pressure exists at the surface because some of you, when I draw in the high pressure here, you're going to be like, well, Aaron, it actually shows low on that weather map. Remember, these pressures are at the surface that they are going to be high. So this is going to be this cold air kind of funneling down in this direction like this. So we can put cold in through here. Now overall, when it comes to these caps of cold air over the polar areas, they also rotate. So we would also have this cold air moving in these series of waves in this direction like that. Cold air moving like this, but it's also getting pushed this way continuously. So can you see now how earlier when I drew you those idealized blobs right here, that idealized blob moving, we actually have fairly complex blobs moving. But this cold air, remember, is moving in this direction. So at the surface, we might end up with a cold front moving in this direction. Now, conversely, over on this side, well, this cold air is also moving forward. So here, this cold air is retreating from this spot on the Earth. So as a result, we could maybe say that perhaps a warm front starts to develop in here. Depends on whether it starts to move or not. So you can see now how we're starting to develop the principle of cold air motion determining how the fronts work. Now we've got a series of waves as well. What you're going to see in a little bit is we're going to see how we can end up with what are known as frontal depressions and how those will start to form more advanced types of fronts. Now, before I go on, what I want to do is just show you one more view, and I'm going to quickly do this just because earlier, remember how, I'll go back to that inset. I probably should have quickly drawn you. So here's that inset that we drew a little while ago. You remember the cold front like this. I think it would have been a good idea to have earlier drawn for you a three-dimensional view, because here's the cold, and then we had that mixing zone right in here. What I want to do is now we can kind of pick this area here, and we're actually going to take a look. Remember, this is in 3 dimensions. So what we're going to do is we're actually going to take a look at this mixing zone in 3 dimensions. Okay, so let's draw this here. We'll imagine that this is the surface of the Earth. So I got something like that. We kind of did a cutaway bit here. So what this would look like right here is something like this. We would actually have this blob of cold air rising up above the surface of the Earth, something like that. And then along here, we would have our cold front moving. So there's the front itself. And then, of course, this is going to sweep up into the sky as well. Remember, from this point now, we have our mixing zone. So the mixing zone is going to look something like that. And this is going to go, of course, in behind something like that. So what we have is from here to here, we have that mixing zone. But don't forget, the mixing zone also exists from the frontal plane backwards and to a depth. Once we get to altitudes here, you can see that the mixing zone, it has a horizontal depth, but it's also going to have a vertical depth. And I just about drew that off the edge of the diagram there, but you can very clearly see that. The overall motion, of course, of the cold air is going to be in that direction. Okay, so I think that's gotten ourselves onto a pretty good start. So let's go back to the presentation for a few moments now. All right, so Rossby waves, let's go back to fronts. I think we've done a pretty good job of describing this part here. It might initially seem confusing, but the movement of a front is always dependent on the motion of the cold air that is perpendicular to it. As you will see, the name of a front is always determined by the motion of this cold air. Yeah, we've shown you that on the whiteboard there. The motion of the cold air will then allow the advancing air mass, or the advancing air, not the advancing air mass, the advancing air to be given its name. On a weather map, these zones are marked, and you've seen that as well. It is important to remember, don't forget this please, as a pilot, this is really important that you remember this statement right here. It is important to remember, however, that since these zones are transitions or mixing zones or frontal zones, that the actual weather will exist many miles ahead or behind this position, depending on what type of a front you have. Remember, cold fronts, the mixing zone, follows behind the front. So when the meteorologist draws that front on that piece of paper, like we did on the whiteboard, the frontal weather will happen behind that position on the weather map. When it comes to warm fronts, and the meteorologist draws the warm front on the map, guess what? The weather actually happens significantly ahead of that warm front, and it typically ends somewhere near where it has been drawn. This will make a little more sense as we start to look at fronts in 3 dimensions. All right, so when it comes to the types of fronts that we have, they are many and they are varied. You've already been introduced to the concept of the cold front, and we've already seen that that's what a cold front looks like on a weather map. The warm front, we've seen those drawn out. We've also seen what we would call the stationary front, so right down here. Now, other types of fronts that we can encounter include the occluded front, and in this case, that's where fronts have started to mix themselves up. They're all jumbled. So occluded fronts look like this. Notice stationary front, the barbs and the warm zone alternate. When it comes to occlusions, they're shown on the exact same side. Now, quite often in Canada, I shouldn't say quite often, occlusion tends to be a little bit more of what an American will show on their map. As Canadians, we tend to show our occlusions as a trowel, and it looks like this on a weather map. Now, don't get all confused. An occlusion is actually the exact same thing as a trowel, and we'll start to describe that later on. It's just in Canada, we tend to prefer using the term of trowel. Finally, we have upper fronts. Now, when it comes to upper fronts and what they would look like on a map, simply what the meteorologists would do is they would not color these in. So this would be an empty triangle if it was an upper occlusion, and then this would be an empty warm semicircle. Same thing for a cold front. If it was an upper front, this would be empty. Upper warm front, those would be empty as well. The meteorologist would not color them in. So you've been given a very good conceptual introduction as to how all of these fronts start to work. You can see right here, we've got something that says the life of a frontal system. And it's not too bad of a diagram, but what I want to do is I actually want to go over to the whiteboard to expand on this a little bit. Here's some key things. Cold air here, warm air here. Then we've got a stationary front. Notice how we actually have a wave starting to develop. And then this wave gets deeper. And in this case, this here would be what we would call a stable wave. Now, if the atmospheric conditions are right, a wave can become unstable and it can become what is known as an occlusion wave. And that is actually what's being shown down at the bottom here, particularly so in this section right here. All right, I'm going to go back to the whiteboard and I'm going to show you this again on the whiteboard. Notice in the end how we end up with the exact same scenario beginning to end. And really what we can think of is we can think of this cold air and warm air trying to mix to balance things like temperature out. That's what the purpose of fronts are. They never really succeed in doing that, but that's what they're trying to do. Mix everything up so that everything becomes the same. Okay, back to the whiteboard we'll go. So now that we're back at the whiteboard, what I want you to think of is these two highs right here. Okay, so this high over here, remember, we said it was continental Arctic. This high down here of warm air, let's say that it was maritime or is maritime tropical. Okay, got it? All right, since you got that, let's erase this. So we're once again going to go to a weather map view. So a bird's eye view, looking straight down. So if I do that, let's first of all maybe draw out our weather map zone here. So we'll draw our weather map here. Give myself lots of room for this one because there's going to be a lot happening in here. So what we'll first do is we're going to imagine that we've got these two highs. So over here, I've got my cold high. So right there, remember, continental Arctic air. And just for the sake of, well, if I put too many isobars in here, it's going to get a little bit too complicated. So I'm just going to draw in a couple of isobars maybe. Maybe one more set. Okay, I think that's good enough. On the other side of this, we've got way down here, we've got our nice maritime Arctic air. So here's the high here, or not maritime Arctic, maritime tropical. So that's nice and warm, right? So in this case, we now have a bunch of isobars as well. Again, I want to be careful because if I'm not careful, this can get a little bit too complicated. Now, we're going to concentrate on this zone here. This is where the two air masses are meeting. Okay. So if I look at this zone here, first of all, what I want you to remember is this. When it comes to high pressure, think of the winds and the pressure gradient force. But remember, aloft at 3,000 feet, it's going to follow these isobars perfectly at 3,000 feet, right? In a clockwise fashion. But at the surface, surface friction allows this to kind of move in this direction. So what we have here is we actually have a zone where this air is trying to push towards this warm air. Here, again, the same thing is happening on the other side. We've got that clockwise flow, but slightly bent to the left of the isobars. So here's what's happening in this area here. If I was to draw like a perfectly straight line between the two, of course, what's going to be happening is this cold air is going to be trying to push in that direction. Notice how the overall wind flow, here where the two fronts are starting to bump into each other, is pretty parallel. But there is a little bit of curving in this direction towards this warm zone. Over here, of course, I've got this warm air trying to push like that. So what's happening here in this zone is I'm ending up with a stationary front. This front really can't go in either direction. So I've got the warm air pushing in this direction, the cold air pushing in this direction. I've got this air flowing like that. It really can't do anything. Okay, so what we're now going to do is we're actually going to take a look at this section here, and we're going to zoom in on it to see what is actually happening there. Okay, so you've got the big picture. Now, let's start to tighten this picture up just a little bit. Now, to make things a little bit clearer, what I'm going to do is I'm actually going to eliminate the black line. And we're just going to draw in the cold air like this, trying to push in that direction. On the other side, we are going to have the warm air trying to push right back. So here's our stationary front. Remember, warm air is here, and then we've got the cold air up over here. Remember the wind flow. So in this case, around like this, and then it's kind of like this and trying to push that way. This flow is kind of like this, and it's trying to push that way. So wind in this direction, wind in this direction. This is what always happens at a stationary front. You have the winds almost roughly parallel in totally opposite directions. The high swirling this way and the high swirling this way. What I want you to next think about, though, is if I happen to be an air parcel somewhere right here, let's say perfectly right there, I'm an air parcel here, or maybe a little air parcel here, or a little air parcel here. Because of this flow, what's going to happen is I'm actually going to start to rotate a little bit. I'm going to get pushed one way or the other. So, again, kind of taking this, imagining this is a parcel of air. Well, my upper hand is moving backwards. This hand is moving this way. So can you see how that flow, notice how we start to develop a counterclockwise flow in here. Well, that's kind of interesting. So I've got a counterclockwise rotational flow developing in between these two fronts. So we'll draw that counterclockwise flow, trying to get going. Now this is from the top-down view. What I now want to do is look at this from the side. All right, so let's look at it from the side. Here's the surface of the Earth. And then somewhere up over here, I've got this high pressure zone. Remember, that's going to be the cold air sinking. It's going to strike the Earth, and it's going to move in this direction. So that's the cold air going towards the warm air. Now, out over here, of course, I've got the opposite happening. High pressure system over here. I've got this warm air, and it's going to be working its way along the surface towards the cold air. Well, guess what? When these two parcels of air meet, now that they're converging, what are they going to have to do? They can't go anywhere else, but this air is going to start to rise, and as well, this air here is going to start to rise. But remember, the wind flows are going to be counterclockwise now. So this flow is going to be like this, and it's going to be like this, and it's going to be going like this, all the way up towards the upper atmosphere. So what's that going to do to the pressure here? That's going to cause this pressure to drop. And it is going to become a low zone. So here we have the air rotating and converging. Now, this is a bit of a very complicated discussion, to say the least, what's next. So I'm going to simplify it by actually, admittedly, just ignoring a few things. What will happen is aloft. You remember those Rossby waves? What can happen is some sort of a disturbance can actually cause this stationary front to start to give the warm air a little bit of an additional, not the warm air, give the air on each side a little bit of an extra push. So the cold air over here gives a bit of an extra push over here, and then the warm air ends up giving it a little bit of an extra push over here. So now, right in the middle, right here, I have this all swirling counterclockwise. I also have it being pushed upwards into the atmosphere. I've got an extra push on either side of this. So guess what's going to happen? On either side, we're now going to have warm air pushing harder on this side. So, as a meteorologist, what I would then do is I would say, okay, we've got a warm front now. That cold air is retreating. So let's draw a warm front right in here. Meanwhile, on this side, I now have the cold air starting to push ahead. So if I'm a meteorologist, I'm going to be, okay, well, on this side, we've got the cold air. It's got enough of a push now that it's advancing. So let's draw the warm front on this side. So this now is a low pressure area. And what I'm going to find is this is going to start to turn itself into a bit of a wave. The cold air is always very fast. Remember, it's very dense. So the cold air is going to move really, really fast in that direction. The warm air, it tends to plod. Warm air is not very dense, so it's a little bit more lazy in terms of moving. So the speed of a cold front is typically very fast. The speed of a warm front is typically very, very slow. Okay, over time, what will happen? So this is time 1. Let's say later on, time 2, what we would find is that the frontal system would look something like this. I'd have my cold front like this, because it's moved very, very fast. Here's the center of the low itself. And then I would still have this warm front like, yeah, I'm in no hurry whatsoever. So it might look something like that. Over time, this cold air continues to rush really fast in this direction. And it is possible for this cold front to eventually continue so quickly that it actually ends up catching that warm front. And this will actually close up like a zipper. You're going to see that's how we develop occlusions. Okay, so I think we can go back over to the presentation now then. All right, so there we go, the life of a frontal system. Here's that wave, cold front here, we've got the warm front here, and then here it is, you can see just folding itself up like a zipper. All right, so let's examine these fronts individually now. We're going to start out with the cold front. Remember, the leading edge of a cold air mass, also known as the transition zone, where the cold air mass is replacing a warmer air mass. This forms when a wedge of cold air forces its way under a warmer air mass, also called frontal lift. Now, cold fronts will typically have a steep slope. 1 degree to 1.5 degrees is not uncommon, and they do tend to move much faster than warm fronts because cold air is exceedingly dense. Many cold fronts can move at speeds of up to 30 knots or more. Now, this slide doesn't mention as well, but the typical depth of the leading edge of a cold front is usually not that big. It's usually about 50 nautical miles. So I think what I'm going to do is we've got some diagrams here, but I think I'm going to go back over to the whiteboard. You can see the warm air mass on this side. These temperatures here are in Fahrenheit, obviously. Colder temperatures back here, again in Fahrenheit, and you can see that cold air pushing through. Now, looking at it from the side, and we'll go take a look at a three-dimensional view in just a moment, you can see this warm air here. And you remember that principle of cold air blobs moving around in terms of air masses? Well, look at this cold air blob. You can see that it kind of comes down and sinks and then moves ahead like that, undercutting the warm air. Okay, let's maybe go to the whiteboard, and I think what I'll do is I'll actually draw both of these fronts out for you on the whiteboard. I'm going to jump ahead and maybe move to a warm front as well. All right, so let's look at the cold front first in terms of what it would look like in 3 dimensions. So we'll draw the surface of the Earth first to start. So there's the surface of the Earth here, and give it a little bit of a depth here. And maybe perhaps we've got something like a city waiting way out here, and it's like, I don't know that I want this cold front to end up coming in this direction, but poor city, it's going to happen. So our cold front then would look something like this on the surface. So we will draw, as a weather person would, that diagram. Now, as you've seen, when it comes to a cold front, typically has a fairly steep slope. Now, this here is going to be 1.5 degrees approximately. So this is the world's biggest 1.5 degree slope. In terms of distance, remember, from here to the point where that frontal zone or mixing zone ends, if I was to give you a distance, typically it's about 50 nautical miles. Now, sometimes as well, you'll hear 1.5 degrees. You will also hear this published in a different way. Typical slope is about 1 to 100. So what that means is for every 100 miles I go in this direction, I'm going to have 1 mile of altitude. Okay, now I'm going to draw in, actually, yeah, I think that'll work. I'm going to next draw in what's happening in terms of the warm air. Now, remember, the cold air is moving in this direction. So this is that cold, dense blob of air moving in that direction. Now imagine from the warm air's perspective, this moves fast. It's really dense air. So this warm air that's here, as this plows forward, if I am warm air, to me, it's going to seem like, all right, so here I am as the warm air, and then suddenly I'm going to get thrown up over top of this cold front like that. So it's very, very abrupt if I happen to be warm air, and it's very, very sudden. Now guess what that is going to do? You remember that principle of when we were talking about stability and instability? And you remember how we were like, well, imagine if I let a balloon go. So we'll just imagine a hot air balloon here. If I'm a hot air balloon in the vicinity of the cold front, I'm going to find that I'm going to get pushed up very rapidly like this warm air is. So I'm going to go up incredibly fast. So what this will do is right in here, just along the entire edge of the front, it's going to create potentially very, very big, tall clouds. And those clouds are maybe even going to start to pour some pretty heavy rain. In terms of cloud types, I'm definitely going to get at least cumulus. Most likely, I would get maybe, say, TCU, towering cumulus. Perhaps, in the extreme form, I might get cumulonimbus. Now, what about the clouds after the front has passed? Well, if I think about the TCU, CU, CBs, well, the clouds will continually get higher because the slope steepens, right? So if I'm the city, this moves over top of the city. I initially would see these thunderstorms coming, and then after the thunderstorms have passed, what I would next see is I might see clouds like maybe some nimbostratus might be in there, but definitely I'm going to see some altostratus, and as well, eventually probably way up here, I'm going to see some cirrus clouds after everything has passed by. So that is an example of our cold front. Brr. All right, maybe not cold enough for icicles. So let's now maybe take a quick look then at the opposite. Let's erase this. And now let's look at our warm front. So warm is going to be next. Draw a little bit of toasties for us, nice warm radiation. There we are. Okay, this one is going to be the front that most people think, oh, these are going to be great because the temperatures are going to warm up. Well, yes, that's generally speaking true. But the problem with warm fronts is they tend to bring weather that lasts quite a long time. So here's our surface of the Earth in this case. Now what happens? If I'm cold or warm air moving in this direction, I can't really effectively push the cold, dense air out of the way. Remember, I have to wait for that cold air to move out of my way. So the cold air is going to be over on this side. And it's just sitting there, and it's not wanting to really go anywhere unless if it wants to move on its own. So as the warm air, I'm kind of going in this way, waiting for the cold air to move, and if I do get to move a little bit, I'm going to ride upwards. So with a warm front, if we were to draw a warm front on the surface, so there's our surface zone first of all. But now, let's imagine what this would look like. So it's going to kind of try to override that cold air. Something like that. Now, this slope here, when we look at this slope, it's typically only going to be 0.5 of a degree. Very, 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 very shallow. Okay. If I'm the warm air, remember, as we've discussed, so here I am, the warm air, I'm moving towards this cold air. Suddenly, surface of the Earth, cold air there, and now I am pushed up, and I'm pushed up very, very slowly. So that's something like what the warm air would look like as it moved up from the surface of the Earth. Okay, so what's this going to do to me in terms of clouds? Well, imagine that I'm the city, again, way out here. All right, and I'm waiting for that warm front to head towards me. Warm air getting pushed up over top, so what I'm most likely to see is ahead of the front, I am likely to see cirrus clouds way up top. So there's our cirrus clouds forming. Meanwhile, if I do start to get some sort of other clouds, they'll get lower and lower. So I might end up with, say, something like maybe along this zone here, I might end up with something like perhaps a altostratus type of a cloud. Up here, I've got cirrus, altostratus. Moving down the surface of this slope, well, the clouds are going to get progressively lower. So they might end up being something like, say, nimbostratus down here. Maybe down here, I'm going to end up with a pure type of stratus cloud. Now, in terms of where we have the frontal zone from the surface, notice how it's going to be all the way up here. I might start to get some rain falling way up here. So this city actually gets some rain falling towards it fairly early. And as that rain falls, I'm going to end up with maybe another lower level of cloud layer right in here. And then eventually, a very low layer of cloud right in there. This distance here can sometimes be as great as 600 miles, but I'm going to put 250 to 600 miles. In terms of the slope, typical slopes for a warm front are 1 to 150 to 1 to 250. Now, this slope idea, particularly when it comes to warm fronts, common exam questions go something like this. Let's imagine that I'm an airplane and I'm flying here and I'm flying towards this frontal surface. Well, notice how I'm not actually going to encounter the clouds and weather until I hit the slope of this front. So the surface is right here. So my airplane is at the surface. Or no, it's at the air. It's 6,000 feet, we'll say. 6,000 feet. And now it's over the front at the surface. But I don't actually encounter the weather associated with that front until much, much later. Until I'm actually somewhere behind the front itself. So imagine a plane now at 12,000 feet. So this plane again, same thing. It's flying towards that frontal surface. Well, on the surface of the Earth, look at how much later they start to encounter the weather. So a very common exam question will be this. They will say, you have a warm front with a frontal slope of 1 to 150. At what point will you encounter the frontal weather? So that being the case, I would look on my map and I'd see there's the surface. But maybe I've got another little town over here, and that's typically what the exam will do, is they'll say, at what town will you encounter the weather? Or what point on the map will you encounter the weather? So what I need to do is mathematically do this. I need to go, okay, well, it's a slope of 1 to 150. So what that means is for every 1 nautical mile of height, I am going to need to travel across the ground 150 nautical miles. So in this case here, for this pilot, if I do the math, well, 6,000 feet, that's very close to exactly 1 nautical mile, a slope of 1 to 150. So that means it's going to be 150 nautical miles, so I'm going to be at town A. Meanwhile, this pilot is at 12,000 feet. Again, using the same math, 12,000 feet, that's pretty close to 2 nautical miles in terms of height, right? So that means I'm going to get 300 nautical miles. So this distance to this next town is going to be from here, where the pilot started, keep flying. This now is going to be 300 nautical miles. Okay, so that's how you deal with questions related to slopes when it comes to fronts. All right, I think that's a pretty good introduction to a 3-dimensional warm front and a 3-dimensional cold front. So I think what I'm going to now do is go back over to the presentation, and we'll start to take a look at some of the finer points that I may have neglected to have mentioned. All right, so cold front, we talked about that. Here's another example of a cold front as viewed from the side. So a few things to notice here. Again, we've got this cold air kind of pushing underneath. Notice the clouds right here. They show cumulonimbus, so this is a very powerful set of clouds. Very, very unstable warm air, obviously. Notice here we've got the weather diagram that we would actually see on a weather map. So here's the barbs, and then here's the isobars. Now, notice how the isobars always bend and make a V at the front. Really important concept. We've always got a V, so really fronts always occur in what we would call a trough. Now, on the weather diagram, look at the winds. You can see ahead of the front, the winds are blowing kind of from the southwest as I look at that. Notice the temperatures in here. Very high temperatures as I read through the temperatures. Again, it's all in Fahrenheit, but right here, there's the drop. Whoa, I went from like 77 to down to looks like 46. That's pretty serious. Meanwhile, we've got the METARs that are being published here for various cities. Again, this is in the US, so we've got Pittsburgh way out here, we've got Columbus, and then we've got Indianapolis, and we've got St. Louis. So as I look at the Pittsburgh METAR, I can see that it's showing that, well, it's obviously a very hazy day in Pittsburgh. Very warm air, very hazy. So it says 3 statute miles, and it does say that there is a little bit of smoke there. All those steel mills going, I guess. Notice the winds. They're out of the south at 12 knots. And then as we get progressively closer to the actual frontal zone itself, look at how the weather changes. So I can now see that it's hazy in Columbus, so it's clearing a little bit. I still have the winds kind of out of the southwest at 12 knots, so it hasn't changed a whole lot. Now, where the front is itself in Indianapolis, take a look at this here. 200 at 24 knots, so the winds have just gone crazy. Meanwhile, we've got 3 miles in heavy thunder showers, so that's really looking pretty rough, isn't it? Now, the nice thing about cold fronts is, remember, their transition zone, that frontal zone, is small. Typically, it's only about 50 nautical miles, at most 100 maybe. So the weather typically clears up very quickly after a cold front passes. Not always, but quite often. So St. Louis, which is behind the front that has passed, notice how the winds have totally shifted. Is that veering or backing? If you said they have veered, that's good. Fronts always cause the winds to veer. So they've veered, and they've increased a little bit from what they would have been before. Meanwhile, it's now nice and clear. I mean, look at this. Scattered, and then right here we had overcast as that storm blew across. Okay, so there's each station as well as referenced on a weather map. Another view, this is showing the clouds that typically happen as a cold front passes by. I sort of showed you this on the whiteboard. You can see that we have the cumulus type clouds right on the leading edge of the front in here. And then we might get nimbostratus. Again, it depends on the moisture content of the air itself. More typically, what you might see is some high altostratus afterwards. Maybe a little bit of cirrus, but quite frequently as well, it will totally clear out. Take a look at that right there. Must know for the CPL exam behind a cold front where the warm air mass is moist but stable. All right, so these are definitely the types of clouds you would see. Remember I said nimbostratus? Maybe. That would be if it's very moist and stable. Okay. Cumulonimbus, Probably wouldn't see it in that case. If it's an unstable warm air mass, oh yeah, kaboom, gone. All right. So let's do something a little bit practical now with a cold front. And let's look at what they actually look like on a GFA. So you can see right here, we've actually got the warm front here, and then we've got the cold front right through here. So just as I mentioned, they can often appear in pairs when we have a frontal wave going. So look at the cold front itself. If you look at the clouds, so here's the clouds marked in with these scallops right in here, right? Look at the depth in terms of ahead of the front and behind the front. It's not very wide. Look at this cold front right here. You can see that cold front. Again, looking at the depth of the precipitation. So there we go. We've got the clouds right here and the clouds right here, and then we've got precipitation happening. It's a very narrow band right in there. Compare that to the warm front. Take a look at this. You see that warm front from here to here? That frontal zone, that transition zone, is huge when it comes to the warm front. Now, a few other things with this cold front that are worth noticing is the winds in behind. You can see that it is quite gusty as that cold, dense air comes whipping around here. Notice as well that after the cold front, it looks like the skies in both cases here eventually do clear out. So you can see that there's clear out. Here's a cold front all by itself. We'll come back to this particular type of a cold front in a little bit. But once again, I can see the front here. I can see that the width is not very great. And then also, take a look at these isobars and how they bend and make that V shape. So a little bit of a V shape. This one doesn't really quite show it quite as good. Maybe it wasn't the best cold fronts for us to have picked in that case. Look at the winds though prior to the front here. This front here, whoa, it's moving 40 knots right in there. And it's moving in this direction according to that arrow right there. Look at the winds right here, gusting 35 in that direction. After the front passes, notice how the winds veer right around, and now we've got them approaching from this direction at it looks like 20 knots. So there we go, good example of cold fronts and what they look like on a GFA. All right, if you really, really want, you can memorize these next three tables. Know this. Yes, you're going to get this on the exams. I can almost promise you that you're going to get these on the exams. So these next three tables, you can memorize them if you want, but I'll show you an easy way to remember it in just a few moments. So this is before the cold front passes. We've got winds, temperature, pressure, clouds, precipitation, visibility, and dew point. The exam will then ask you what is going to happen as this front moves. Okay, so before the cold front, notice how the winds are from the south to the southwest. And in those examples that I showed you earlier, you clearly saw that. As for the temperature, yeah, it's going to be reasonably warm. Notice the pressure is going to be falling as the front approaches. In terms of clouds, well, initially it was clear, but increasing cumulus, towering cumulus, and cumulonimbus. Precipitation, short periods of showers, and visibility will be fair to poor in haze, just as you saw with those two cities ahead of the front, right? Dew point, that's going to be very high. Right now, we are in the warm air mass zone, so the dew point is going to be very, very high. Now, next, we've got the cold front. All right, so what's going to be happening as it passes? That's what I meant to say. What's going to happen to the cold front as it passes? The winds are going to be gusty and they are going to veer. Typically, they will increase as well. When it comes to the temperature, well, cold front coming through, the temperatures are going to drop, right? What about the clouds? Probably cumulonimbus. Again, it depends on the stability of the warm air mass. And the pressure. The pressure is suddenly starting to go right up. Precipitation, it's going to be showery because we've got cumulus type clouds, right? And then the visibility, it's going to be poor, particularly if you're caught in one of those showers, but it's generally going to be improving. And then finally, the dew point, well, because the temperature and dew point were lining up to cause that precipitation, we're going to end up with the dew point as that precipitation starts to fall and the cold air starts to flow inwards, it's going to drop. Okay, so what about after the cold front has finally gone by us? Well, as you saw, it quite often will start to clear up nicely. So that said, let's go through the winds first though. Becoming west to northwest, they will veer. And then we've got the temperature steadily dropping. The pressure will be rising steadily. The clouds, as we mentioned, if it's a slow-moving, warm, and stable air, nimbostratus, altostratus, cirrus. Okay, if it's fast-moving and unstable, well, that's where we definitely get the cumulus or cumulonimbus, towering cumulus, right? And then typically it will probably clear out. Precipitation, showers and clearing. Visibility, good, except for maybe in a few of those lingering showers. And then the dew point is going to start to drop. And that is because, well, the temperatures have dropped as well, and that air is clear and cold because the precipitation has fallen. So here's what a satellite image looks like of a cold front. You can see that frontal zone right in through here. So this is the cloud cover, kind of following it. And you can see, like, just, you know, not really very much of a length in terms of that cold front lasting very long. It only covers, like, barely even covers an entire state here. As you get down in here, a couple states, only covers part of northwestern Ontario. In terms of the radar returns, well, this is typically what this would look like. You can see that sharp, short precipitation all in through here as that cold front sweeps forward. And then a few lingering showers here and there, but finally, eventually, giving way to clearer air in those areas. Now, warm fronts. I drew you this on the whiteboard already. Remember, warm fronts are the retreating edge or the trailing edge of the cold air mass. Warm air masses we've seen are slower. The warm air masses tend to go up and over top, less dense air. They gotta go over top of that cold air. The slope of a warm front tends to be very shallow, typically only 1/2 of a degree. Okay, here's a weather chart of, again, and a side view of a warm front. So the warm air is moving in this direction, very slow and plodding, just moving up as this cold air slowly moves itself out of the way. As I showed you on the whiteboard, we start out with very high cloud, cirrus, cirrostratus, altostratus, move down to nimbostratus down here at the bottom. In terms of our cities, still have Pittsburgh, Columbus, Indianapolis, St. Louis. But if you were a pilot flying towards a warm front, you can imagine what would happen. First of all, out over here, clear skies. And then as we move closer and closer and closer towards St. Louis, everything gets worse and the deck constantly lowers on me. Cold fronts are different if you're approaching them. You can usually see the cold fronts heading towards you. All right, looking at our meteorology, you can see here we've got this warm front. Again, look at the isobars. It's more gentle, but there is definitely a V here. The reason we don't have as sharp of a V is because the air isn't as dense. The temperature variation isn't typically as great either. Look at the temperatures. Out here, because I'm in cold air, 53 Fahrenheit. And then as we kind of move towards the front right here, okay, it's jumped up to above, well above 60 Fahrenheit. Look at the winds again. Notice how here we've got the winds coming out of the southeast. And then after the front passes, they again veer and come from the southwest. So winds always veer at a front, always. If I look at the weather out in Pittsburgh, way ahead of the front, I can see 1:30 at 12, 10 miles, so the visibility is pretty good. But look at each one of these cities gets closer and closer to the front itself. Look at how those visibilities consistently decrease. Look at how I go from haze to rain and then to light rain eventually. All right. Ceilings. What about the ceilings? Well, as I mentioned, if you're a pilot heading towards these, I can see here that it's scattered in Pittsburgh, overcast at 6,000 here, broken at 2, and then overcast at 1,000 by the time we get to St. Louis. Here's another view of a warm front from the side, showing those clouds. So, as a pilot, we can end up with two things. And please watch out for this on the exam. Because if I'm going from warm air to cold air, they'll ask what would be the sequence of clouds. Well, typically, I might even be able to fly above them. Probably wouldn't get to my destination because it would be overcast. But in this case, moving from the warm air to the cold air, I would go nimbostratus, altostratus, cirrostratus, cirrus. But if the front was approaching, or I'm flying towards the front, well, from that direction, I'm going to see cirrus, cirrostratus, then altostratus, then nimbostratus. So it's going to continually become lower and lower and lower. All right. Here's some GFA examples. Earlier, we took a look at the exact same diagrams. So now you can see right here, the warm front. This warm front is moving in this direction. Looking at this front over here, again, you can see that front. And then just look at the really bad weather in here in this extensive frontal zone. I mean, yes, the weather in the cold front zone, so this is where we read all of the cold front zone right here. Yes, the weather isn't great along the cold front. But along the warm front here, goodness gracious, it's even more of a disaster than the cold front. Down here, we've got a zoom in of a warm front. You can see this warm front moving in this direction, and it's moving only at about 5 knots, so it's a little bit of a pokey type of a warm front. Remember, anyways, warm fronts tend to move slower than cold fronts. All right, so go ahead and memorize these if you want. Again, what I am going to do is show you on the whiteboard a method that I find is simpler than trying to memorize each and every one of these. I just remember a single picture. Before the warm front, so way ahead of the warm front, just like Pittsburgh was. In this case, what are the winds doing? They're south from the southeast, maybe even from the east. Temperature, cool to cold, slowly warming. Pressure, falling gradually. The clouds, well, as we've seen, they go from high to low. Precipitation, light to moderate, rain, snow, sleet, or drizzle. Oh, exam note here. These types of clouds are formed by the warm air expanding as it is lifted by the retreating cold air. Okay, so that warm air moving up, we end up with the latent heat being released, and then we end up with it condensing and then eventually falling as rain. Okay, so precipitation, visibility is generally going to be poor, and that's because, remember, lots of moisture. Dew point, it will slowly rise. Now, some of you might scratch your head and be like, well, why is the dew point rising? When we look at the next diagram that I use on the whiteboard, you'll see why. So the warm front reaches us. What happens as the warm front passes? Okay, the winds, variable and veering, the temperature, steady rise, the pressure, it's going to start to level off. Clouds are going to be stratus type, maybe nimbostratus, drizzle or none in terms of precipitation. Visibility, poor but improving, and the dew point is going to stay fairly steady. Now, after the warm front has passed, what's going to happen? Winds will become a south to a southwest. They will be warmer than steady in terms of temperature. Pressure, slight rise, followed by a little bit of a fall maybe. Clearing, precipitation, commonly none. Maybe there'll still be a little bit of light rain hanging around. Visibility, that's going to be a little bit hazy because now we're in the warm air mass side, and then the dew point is going to rise but be steady. Okay, so go ahead and memorize those tables if you want. But you know, I've always found it easier just to use a picture to remember what's going on. And because we've taken such great care to study these blobs and what they look like as they move around, and the front and what a front looks like as it moves around, or a low, I should say a frontal depression, we'll go to the whiteboard and do this together, and then you'll see, I think it's a little bit easier. Okay, so I'm going to erase our picture of our warm front. And what we're going to do is imagine a weather map. So the top-down view. And when I do the top-down view, it's going to be a little bit simpler to help you remember what's going on. So let's draw an ideal frontal wave. So we've got the low pressure system right here. So that's going to be right in the center. Then, of course, as we've seen, we have the cold front sweeping off like this. And we will draw that like that. Then we also have the warm front over on the opposite side. So we will put the warm front over here, and we will give it something like this. All right. Next up, what I want to do is I actually want to draw in the isobars. Okay, so whenever we have this zone here between the two fronts, it's kind of interesting because the isobars will go almost straight across. Around the low, the isobars will look something like maybe this. So let's start to draw it on the cold air side, those isobars. Okay, now, as I said, between these two zones here, the isobars typically join straight across, something approximately like that. Few things to remember here. When it comes to the wind flow, it's a low, right? So the wind, pressure gradient force, is going to make it head towards the low, but also remember they're going to bend into the left towards the low. So my wind flow would look something like this. So way out here, my wind flow out here is going to look something like that. All right, wind flow something like this out here, wind flow something like this out here. So now what we're going to do is this entire low is going to be moving in, let's say, this direction, something like that. Lows will usually move in the same direction as these isobars between the fronts. So this low is probably moving in this direction then. Now what I want you to do is I want you to next imagine a city. Now we're going to start this city here. This will be city A. However, because this low moves, at some point as it moves across, actually, you know what? It'd probably be better if I put this city not here, just to represent this a little bit better. It'd probably be better if I put the city here. It'll be easier to see what's going on. So the low moves in that direction. So we're going to end up with the city here in a little while. And then finally, going to end up with a city here. So this is position 1, time 1, so T1, time 2, time 3. So this is a city that has the cold front pass it. Over here, we'll have another city. And we'll imagine that this city is right here. So this is going to be T1. Then as the front passes, that will be T2. And then finally, T3 as that passes. So let's imagine city number 1. So this is going to be the cold front. Our low, we'll say maybe it has a central pressure of 920, just so that I can keep the math simple. So these isobars are going to be 924. This one's going to be 928. This one's going to be 932. This one here is going to be 936, because 4 millibar intervals, right? Now let's start to think next about our temperatures. So in here, I have the warm air mass, right? There's the warm front. The warm zone is going to be in here. And then over here, of course, I am going to have the cold air mass. So that being the case, the temperatures over here, let's say that the temperature over here is maybe, let's say 10 degrees Celsius. In here, perhaps the temperatures maybe are 25 degrees Celsius. That makes sense. It's warm. So this town over here is probably going to be encountering pretty close to the same temperatures, 25 degrees Celsius. But let's look at city number 1. So time 1, this is prior to the front. What are the temperatures? Well, they're nice and warm. Pretty easy to see. What about the winds? Well, if I look at these winds here very closely, I can see that they are going to be coming out of the south. What about the dew point? Well, very, very warm air. So as a result, I might see something like a dew point of 15 degrees Celsius. All right, what about the weather conditions? Well, I'm not anywhere near the front, so the weather conditions are going to be fairly clear. What about the pressure? Well, in this case, it looks like I'm on the 928 isobar, so my pressure is going to be 928, but as this front moves, I can see how I'm going to slide into a zone for a little while where the temperature, or not the temperature, where the pressure is starting to drop, because I'm going to get closer to the middle of the low. So the pressure is dropping. Okay, so that's prior. What about during? Well, the temperature, as I'm here at T2, that temperature is going to suddenly drop. What about the winds? The winds are probably going to pick up, and then, looking at these isobars, they go from a direction of about 210 to suddenly, oh my goodness, those winds are veering right out of the west, so 270. Temperature drops, winds change, they veer. What about the pressure? Well, the pressure is going to drop as quickly as it can right now. It's going to be at the lowest point that it can. What about my dew point? Well, remember, for the rain to start to happen, my temperature dew point spread, they've met. 25 degrees Celsius, it's dropped 15 degrees Celsius. They met, all that rain fell, the temperature continues to drop towards 10 degrees Celsius. So what that's going to do to my dew point is, as the rain falls, they're going to be equal. So let's say 15 degrees Celsius. So it starts to rain. That dew point is going to start to drop to maybe, let's say, 12 degrees Celsius. And this temperature maybe right at the front here is also close to 12 degrees Celsius. That's why we get that rain. Pressure, we already talked about that. Weather, clouds and stuff, it's going to be raining. After the front. Well, temperature, it's gone down 10 degrees Celsius. Winds, oh wow, Winds are really coming out of the north now, so they've continued to veer. What about the pressure? Well, now I'm heading towards, remember, out here there's a high, so the pressure now is actually going to start to increase. What about the dew point? Well, the dew point, it has probably dropped quite a bit, 8 degrees Celsius, and it will probably remain low. Maybe it might drop a little bit more still, mostly because in addition to this being cold air, it's typically also very dry air. So this over here is moist. Now for our town over here, again, you can very easily see what's happening. Prior to the front, look at the winds from the south, southeasterly even. In terms of our temperature, well, it's going to be fairly cool. We already mentioned it is, 10 degrees Celsius over here. So the temperatures are going to be very cool. What about the pressure? Well, the pressure again, same thing. This low is moving in this direction. I've gone from 936, I've gone down to 932 as I approach the front. So the pressure should also be dropping. All right, what about the weather? Well, hazy, right? Once I hit the front, what do the winds do? Well, you can see very clearly that now the winds are going to flow something like this. So they go from here where it's maybe 150, now they go from where it's say 210 as we talked about earlier. So they have definitely veered. The pressure, well, it's going to be a slow drop as that front passes. Isobars, remember, they're a little bit more gentle than on this side. So you can see very quickly how this diagram will allow you to very quickly talk or to accurately discuss what is happening in terms of a frontal passage. All right, so let's head back over to the presentation now then. Phew, boy, have we covered a lot, huh? Maybe it might be time for you to go have a quick little break, off your chair for a few moments and go grab your favorite snack or something like that, because we still have quite a ways to go. There's lots of stuff when it comes to fronts. All right, done that? Good. Okay. Now, one tricky type of front is the winter warm front. And boy, oh boy, as a pilot, do you ever need to watch out and pay attention to these. They can bring all sorts of nasty things. Now, when it comes to the written exam, you need to think very carefully and very cautiously with winter warm fronts because there is so much that can happen. Here we've got this warm air here moving in this direction, and you can see the cold air over here. So we've got the frontal slope right here, so you can see that warm frontal slope there. But there's one part of the equation that makes things exceedingly difficult in the wintertime, and that is the type of precipitation that we will encounter. Now, think of it this way. Remember, warm air, let's say that the temperatures on the warm side are above freezing. So, starting at the surface, as we start to climb upwards into the sky, remember the lapse rates tell us that we're going to end up with the temperatures dropping. Eventually, we will reach a point where we hit the freezing level. Now, for those of you with a commercial exam, they might ask you to figure out what this freezing level is, perhaps. For anybody else, keep paying attention. This freezing level, of course, is going to be at a constant altitude moving towards the frontal slope. And you might remember that airplane that I drew earlier asking, well, when do we encounter the frontal slope? So wherever the freezing level strikes the frontal slope, remember there's also going to be cold air on the other side of that slope. So typically with the cold air below freezing, it's now going to follow this slope backwards towards the surface again. Now when it comes to asking yourself what types of precipitation are we going to get, it's going to depend on where it is that you are flying. So let's imagine an airplane right here at this altitude. As it flies from warm to cold, it's going to be in here and it's going to encounter clouds and then rain, and then eventually it's going to be boom right into the freezing rain. Now when it comes to the freezing level, anything above the freezing level is going to be frozen if it's precipitation, so that will be snow. But let's say the snow is falling down. Once it hits the freezing level, now it's going to turn into rain in this area in here, right? But think of this. We now have that frontal slope, and below that frontal slope, the temperatures are freezing. So we start out with snow, it falls, we end up with this snow partially melting, turning into rain, and then freezing suddenly. Well, not freezing, but staying super cooled and ending up as freezing rain. So it won't actually freeze until it strikes something. Now, what if we're a little bit further down this way towards the cold air? Again, if it's falling as snow up here, it's going to fall through here, partially melt, and end up becoming what we call pellets. They're kind of like frozen blobs of rain. Almost, they look a little bit like mini hail. So, in this case, pellets would be found in through here. Now, if we continue this way, of course, it's going to be entirely snow. So if I'm flying in this direction at this altitude, I would have rain and then freezing rain. Heaven forbid, that's going to be miserable to your airplane and very dangerous. And then it would turn into pellets and eventually turn into snow. If I'm an airplane approaching it from the other direction, though, from the cold side, well, I'm in snow, and as I'm in snow, I suddenly start to encounter pellets. So I hear plinking on the side of my airplane, and I look out and I'm like, oh, that's not snow anymore. That's little frozen balls of snow, little frozen, looks like mini hail. It's going to be next. Pretty much promise you it will be freezing rain. So read these questions related to the winter warm front carefully. And what I strongly suggest you do is, just as I showed you a few minutes ago with frontal passages, commit this picture to memory. Most specifically, remember the freezing level and the frontal slope. Remember, over here it's snow, and then over here it's snow as well. So to the far right, into the cold zone, it's snow. Far above the freezing level, it's also snow. In your mind, remember that it turns to rain. But after the frontal slope, as it continues to fall, whether it's freezing rain or pellets will depend on how far I am into the cold zone. Once I've drawn this out, and you can see somebody here drew it just slightly differently. Once I've drawn this out, now I can put my imaginary airplane into this picture and start to fly my imaginary airplane around. Don't keep it in here for too long, though, because it'll just fall to the ground. Freezing rain tends to do that to airplanes. Okay, winter warm fronts, good enough. I think we got it. Okay, so here's another diagram of that, viewing it from the top down. Now, we threw in here a picture from the GFA, so we'll actually zoom in on this right now. And this is out in the Newfoundland area, so where they get some pretty powerful nor'easters. So in this case, you can actually see this warm front right here. And yes, it was in the wintertime, and you can see how it's moving in this direction. Now, what I want you to look at is how this actually perfectly fits the model that we have just drawn out. Because look at way ahead of the winter warm front here. I've got clear skies, and then as I look at the ceilings, as I move towards the front, the ceilings continually drop. So that being the case, I know that the model that we've been talking about is correct. Now look at way out here, way out far ahead of the front. Light snow, blowing snow. Okay, so all right, sounds good. As we approach the front though, it continues to be snow, but look at what happens right in here. We now have the symbol for pellets right in here. And then it shows slash freezing rain. So I would expect the pellets to be in here, and then I'd expect the freezing rain to be right in about here. Now, as I go through the front, which you probably wouldn't be able to do very easily, if I go through the front, look at how on the other side of the front, when it's in the warm zone, look at how this is all rain. I mean, the weather still isn't that great if you read through here, but light rain, drizzle, light rain, light showery rain over and over and over again. So perfect. Snow, all right. Then pellets, then freezing rain, then straight rain. Now, don't forget, there's 3 dimensions to this, however. Let's imagine that I was above the freezing level. So if I'm above the freezing level, what kind of precipitation would I encounter? That would be snow. All right, let's maybe take this off. There we go, and we'll continue on. So now what we want to talk about is where we have an unstable wave. So we have a really fast cold front, very dense air, very cold, and what it has done is it starts to race around and eventually catches up to the warm front. Well, that's going to produce some pretty crazy weather on us. This is going to produce what we call an occlusion. Now in Canada, an occluding front is often called a trowel as well. So here's the first step. Cold air racing ahead, it's going to catch this warm front. So there we go. It's done that. So what now happens is we start to have the zipper effect. Here's this cold air moving in, and notice we've got cold air over here, so the two have circled around and met. The warm air now starts to get forced above that pool of cold air. So there we go. That would be from here in up through here. Occluded front. In Canada, we would draw this as a trowel. Here's what an occlusion looks like from the side, and boy, oh boy, poor Indianapolis. When we have an occlusion happening, quite often what will happen in terms of weather is it's going to be a combination of like a cold front and a warm front, right? If we tend to be on this side, it'll look a little bit more like a warm front, the occlusion. But if we tend to be on this side, now it'll look a little bit more like a cold front. However, it is possible to be right exactly in the middle, like Indianapolis, and to get the both of them. So just imagine the horror of living in Indianapolis right now. In Canada, as I mentioned, we use the word trowel. This is short for a trough of warm air aloft. And our symbol, here you've got the cold front here, we've got the warm front here. You can see here's where the zippering is happening in through here. So this is the trowel right in there. What I want you to notice is that in this sector here, kind of north and northeast of the trowel, is typically where the weather is fairly intense. It can also continue on, though, along the trowel itself. But more commonly, kind of this north-northeast sector is the area that gets the worst of the weather. And reading this GFA, you can tell that. Hey, look at this little tight frontal zone here. Oh, look at this warm front. Oh, wide frontal zone there. Okay. Whenever we have a trowel, we need to remember that we actually end up with 3 air masses because we've got the cold air here. Typically, we have the cool air over here, and then we have the warm air right here. Okay. All right, the clouds and precipitation are going to depend on the moisture content of the warm air. The more moist the warm air is, the worse the weather at the trowel would be. As I mentioned, it can be a combination of both warm front and cold front. Technically, the cloud pattern ahead will be similar to warm front, and the pattern that trails will be more like a cold front. Okay, I mentioned that. All right, and this I mentioned too. Okay, right on. Now, when it comes to the 3 air masses that we have at a trowel, I did mention this as well. We're going to have a cold air mass, so this is the one back here. And then we are going to have a cool air mass. This is the one in over here, just ahead of the warm front. And then we've got the warm air mass in here that's getting pushed aloft, okay? Here's another diagram of an occlusion. This one's a little bit nicer. You can actually see it's slightly 3-dimensional. So there's the trowel right there. And then it just shows the cold air coming up to the cool air, the warm air here. So there's our three air masses. You can see over time it's starting to zip up. So there's the cold air and cool air meeting. And then bang, up goes the warm air. And now we have all sorts of interesting weather if you happen to be a city somewhere right in here. Okay, so what got all of this going? We didn't really talk about the stationary front. This GFA here shows an extensive stationary front covering all of Manitoba right through the Dakotas. And actually, if I remember correctly, this one went almost all the way right down to Texas. So it was a huge stationary front. Notice that stationary fronts, remember, they're where two air masses haven't really decided whether they're actually going to get moving yet. I should say the cold air hasn't decided that it's going to get moving yet. So in this case, you know, we've got these air masses just saying, you want to go anywhere? No, I don't want to go anywhere. Notice the weather here, because they're kind of just meeting each other and just kind of stuck there. Typically, we don't have really good weather along a stationary front. You can see as you read in through here, on this side, it's not too bad, 4,000 feet, 6,000 feet tops. Over here, yeah, definitely a little bit lower for sure. But look at this. We've actually got some freezing rain and some pellets in this zone here. So this over here would actually be the warm side. In here, looks like it's more so snow showers in through here. So I can actually see, looking at this, which one is the warm side over here, looking at the precipitation and stuff. Cold side is here. Pay attention to the barbs as well, because the barbs are pointing this way for the cold air, right? So this is the cold side. This is the warm side. That could very often happen on the exam as well. On which side of the stationary front is the warm air mass? Okay, well, I just did it by reading the precipitation and reading the direction of the barbs. Winds will blow parallel to a stationary front. You can see mostly the isobars are very close to parallel the front. Precipitation, prolonged. Clouds, potentially prolonged. A noticeable temperature change and or wind direction is commonly observed. Remember, this high here, it's rotating clockwise, so I would expect the winds to be flowing parallel to this front from the north. Meanwhile, on the warm side, here's a couple of hints. You can see these isobars, you can actually see these here. So I'm expecting these winds to be coming out of the south, like that. So if I'm an airplane flying from here, and I suddenly cross, oh, good grief, I'm going to have to adjust my course to the right suddenly. Another very common type of Transport Canada exam. As you cross the front, which way will you have to alter heading? The answer is, in any case, it's always going to be to the right. Stationary, warm, or cold. Doesn't matter. The winds always veer at a front. Okay, so frontogenesis, that is the process of a front forming. And then we've got frontolysis, which is the process of a front dying. Frontogenesis, notice how there's just no line between the barbs. Notice here with frontolysis, they're partly taken away. Now, some methods that can lead to frontolysis are when one of the air masses are modified. Remember, we need a big temperature difference for a front to exist. So if one of the air masses gets modified and the temperature becomes similar to the original temperature of the air mass it was meeting, well, front will disappear. Another way is due to a wind field that weakens the temperature gradient along the frontal zone. Let's think way back to the beginning of the presentation. And you remember when we talked about frontal types? Well, another type was the upper front. Up until now, we've mostly been concentrating on fronts that touch the surface. Well, okay, some of you are saying, Aaron, trowels don't touch the surface, and you're right. But when it comes to cold fronts and warm fronts, they could be aloft. And if that's the case, things will change on us a little bit. Here's the important statement. In Canada, an upper front refers to a non-occlusion situation. So for those of you who go YouTubing and stuff like that, and that's good, you can learn lots from YouTube, I want you to remember that you might get information that's from the US or different countries. It gets more confusing, in my opinion, because they often don't very clearly differentiate between occlusions and upper fronts, and it just gets to be a big mess and hard to delineate what's going on. So I like it how in Canada we say must be non-occlusion situation. These will form when air is trapped on the surface and the frontal weather is pushed aloft. Okay, so let's go to the whiteboard for just one moment, and I'll show you probably the easiest example that I can think of where this could happen. So we'll erase our nice low here. And then we're going to imagine a scenario like this. We'll draw kind of a ground zone here again. And this is actually fairly common when it heads out to the prairie, or not the prairie area, but the mountainous areas. So we'll draw in a series of mountains here. So let's imagine these mountains extend as a solid line like the Rockies do. So these are a solid line all the way across. If we had, let's say, on the west or east side, let's say that we had a dome of cold air kind of at the surface. So this is all kind of like cold air. It will often pool itself at the height of the mountains and just below. So if we had this nice warm front that's heading towards the mountains, and it's like, hey, everybody east of the mountains, I'm going to warm the temperatures up for you. Well, now it hits the mountains. And which way is it going to be forced to go? Well, of course, it's going to be forced to go upwards, like that. So guess what happens? These poor people who are sitting on the plains, maybe it's in Calgary, maybe it's well east of Calgary, so way out here. I live out in the Winnipeg area. This happens to us all the time, for crying out loud, in the wintertime. But this warm air goes right over top of this cold air because it's so dense that the warm air just like, I'll just move right over top of it. So we're sitting here in Winnipeg, maybe sometimes in Calgary, and we're freezing cold, but above us, up above us, there happens to be this zone of nice, warm air aloft. It's maddening sometimes when we see that happen in Winnipeg, but for many of us across the prairies, this happens just all the time. All right, so that's one of the simplest cases that I can think of for a warm front. Now, imagine that that warm front goes passing over you like that, and you're like, rats. For you on the surface, what are you going to observe? You're still going to observe some things appropriate for that front, but you're going to miss out on some other things. For instance, winds will shift and veer. It's above us, right? So not really. No. Temperature, is it going to change? No. What about, though, let's say that warm front is producing precipitation. Are we going to see that? Yeah, because the precipitation is heavy, right? So the precipitation will fall from the sky down towards you. So as that warm front goes over top, it frequently leaves a pile of snow for you as well in the wintertime. Thanks. All right. If, however, I happen to be an airplane that is flying at a higher altitude above the level at which that front starts, I will encounter all of the same things relative to as if I was on the surface. So an airplane aloft, if they crossed through a warm front, would they see a wind shift? Yes. Would the person at the surface? No. Temperature. Would they see a change in temperature of the airplane as they flew through that? Yes, they would. On the surface? Okay, so think about that. And questions about upper fronts are really a favorite of Transport Canada when it comes to the commercial exam and the ATPL exams. Now, frontal fog is a type of fog that occurs when the warm air mass, or I should say the warm front, produces rain. Now, I don't really want to describe this because, again, a picture is pretty good. So let's go back to the whiteboard for a moment and I'll show you what this would look like in terms of how it forms. Okay, so goodbye upper warm front. And then let's imagine now this is a surface warm front. So we will draw the frontal slope here like this, something like that. And then I'm going to draw the surface of the front, or the frontal surface, just like that. Okay, so we'll join these two up here. Now remember, earlier we discussed how typically what will happen is we'll get clouds that will form far ahead of the front, so something like that. So this being the case, if this was to produce rain, what will often happen is as it falls, remember this here is cold air down here, right? And it started out toasty warm. So now it starts to fall into that cold air. Well, what will happen is this rain falls into the cold air, it's going to saturate this air. So we'll end up with maybe a lower layer of cloud, something like that. It will continue to fall, and eventually what will happen is as it hits the surface now, we will end up along the surface with fog as this surface becomes saturated and the air just above the surface becomes saturated with that falling rain. So precipitation fog is caused by the moisture from the rain saturating that cold air. All right, so frontal fog. Now, fast-moving cold fronts. Well, we've already seen that they can frequently move very fast. But in the summertime, they can become especially fast-moving. Fast-moving cold fronts are very steep. Cold, dense air that moves ahead rapidly. Warm air is forced to rise violently. You know, as I go through here again, let's go over to the whiteboard again and quickly draw this out because it can produce some pretty interesting weather as well. And we'll elaborate on this a little bit when we get to the section on thunderstorms. So let's imagine from the side this view. So this being the case, we've got this cold air and it's rushing ahead like this at high speed. What will happen, here's the frontal zone right here, is at the lowest levels, this cold air here is going to encounter some friction. So the upper cold air actually moves a little bit faster than the lower levels of the cold air. So this frontal zone will actually start to look something like this. It will end up with what is called a protruding nose. Now this is going to be a very unstable situation. First of all, two things are happening. well, I shouldn't say first of all, there's a couple of things happening here. If we imagine this warm air suddenly hitting this slope as it moves in, the warm air is going to go like this, and then it's going to suddenly be forced upwards, right up into the stratosphere. Meanwhile, imagine this zone here. Well, remember that principle of buoyant air? It's going to be moving upwards. Now it encounters this cold air. It's going to go really, really fast and get a good kick upwards as well. Suddenly it encounters the warm air going up here. So we get a huge kick in terms of speed. So this situation here can become very unstable very rapidly. Cold air over top of warm air, and then over here as that air comes through, suddenly it's got a kick from all that warm air, also pushing it aloft from frontal lift. So fast-moving cold fronts can really, really get things going in terms of summertime thunderstorms. Extremely unstable, very narrow band of violent weather. The wind is going to veer. It's going to be very, very gusty. And yeah, I can pretty well guarantee you that if it's summertime, you're going to get a long line of thunderstorms, known as a squall line. All right, so here's an example of a fast-moving cold front. And you probably saw earlier this when we looked at cold fronts. Now, interestingly enough, if I had looked at D and I had looked at E, remember that's going to be over here on the GFA. We probably should have pasted it in for you here, but there was actually warnings of the potential for thunderstorms along these zones here. Now, to finish, the material as we finish here, a lot of this does start to delve a little bit more into commercial and ATPL levels. So, except for the very last slide, for those of you who are watching, it's probably going to be mostly safe to skip the next few slides about upper fronts. In this case, we just describe them in a little bit more detail. So this diagram here, you can actually see that what we have is, again, we have a mountain here, and we have maritime Arctic here, and then we have maritime polar here, and then you can see how we have continental Arctic down here. So in this case, this is showing us another case where maritime Arctic moving over towards maritime polar, continental Arctic down below. So this actually here is a case where we could have a upper cold front. All right, so yeah, I know you're thinking, well, the air is very cold down here, but don't forget this is overriding that even colder continental Arctic. So some people might be like, well, isn't this an upper warm front then? No, not really, because it's moving maritime polar out of the way. It's doing nothing to the continental Arctic. It's just going to go right over top of it. Okay, so that's a case where we would call this an upper cold front. All right, so remember that diagram, very common on commercial exams to see something like that. Here's another way that an upper warm front could form. I showed you the mountain example earlier. In this case, let's imagine that we have warm air here, and like it does, it's going up over top of the cold air that's slowly retreating. Now, notice though that this has an initial shallow zone, but then over here, it suddenly has a zone where it becomes steep again. If I was a meteorologist, I would actually put the upper warm front right in here, because this is where it suddenly steepens. So I would see two things on a weather map. I would see, first of all, the upper warm front at this point along the surface, and then I would see over here, drawn on my map surface, I would see the actual warm surface front itself. Okay, you will recall that fronts exist because of a temperature difference between air masses. So another way that a upper front could occur is like this. Imagine a case where we've got daytime heating. So if I've got daytime heating, what will happen is it will make it warm at the bottom, right? There might not be a sufficient temperature contrast between the two temperatures at the surface anymore. So then I end up with an upper front as well. And you might be like, what? Wait a minute. How does that happen? Well, imagine this. Initially, cold air over on this side, warm air over on this side, and then imagine this frontal slope right here. Okay, so this is a warm front moving in, right? Well, daytime heating comes along and it heats up this zone here. So this is no longer cold, but this becomes warm. So as a result, the warmer air is forced aloft. So now as a meteorologist, I would draw the warm front in here as an upper front. So here's a couple of examples of what the upper front would look like on the GFA. I can very clearly see right here, warm upper front moving in that direction towards the northeast. And then I can see all sorts of precipitation and whatnot associated with it. If I look at the isobars, notice how the isobars don't really indicate much of a wind change. Remember, the isobars are drawn for the surface, so are all of the fronts. Except in this case, yeah, it's aloft. So over here, got a cold front, upper front specifically, and then a warm upper front again. And once again, you know, as I look at the isobars along those fronts, I can really see that the winds don't shift. Now, if I'm in an airplane flying at the level of the front, then the winds will shift. So watch out, please, on the exams. Are you in an airplane or are you on the surface with that front? All right, to finish, weather at the trowel. Well, we did talk a little bit about how trowels can often be the worst of everything, right? It's a combination of cold and warm front conditions. Remember, please, remember, the cloud pattern ahead of the approaching trowel is most similar to that of a warm front. Cold front cloud formations will exist more so on the back side of that trowel. Very likely, though, that cumulus will build up. Thunderstorms will be interspersed with stratiform clouds, continuous precipitation, and widespread low ceilings. So really, trowels are typically the worst of the bunch. And just to show you that, here's one more example out over the East Coast regions. You can see a very powerful low again. Notice how, in this case, again, it's a wintry season, so freezing rain, severe ice conditions are likely hazards. And this is because the rain aloft in the occlusion, it just gets really messed up. You know that nice diagram that I showed you, the perfect idealized diagram of a winter warm front? Oh, it just gets mixed all up like crazy in these occlusions. So let's zoom in. I use the American term, occlusion, trowel. All right. So yeah, as you look here, like here's the trowel in here. You can see it just tells us freezing rain, lots of dangers, snow, rain, blah, just messes everywhere. Rain, snow, not good. I mean, look at over here. Once we get into the icing section, right in through here, we can see extensive icing, moderate icing, 2,500 feet to 5,000 feet. Looking out over on this side here, again, lots of turbulence as well. Look at the freezing in here, just mixed freezing. So just not very pretty at all when it comes to an occlusion. Really, if you can avoid these, it's probably best to do what you can to avoid as much of it as possible. All right, let's zoom back out. And there we have it. That's the little bit of fronts. Oh, wait a minute. I should mention, very important exam thing, and this is where hopefully everybody who's a PPL, rec pilot, and whatnot are all listening again. When it comes to questions related to at what level is the front, well, you're going to have to probably do some thinking. On the GFA, and on any other significant weather charts, etc., the front is always drawn at the surface. Now, that said, if you're in an airplane, remember you might not encounter that particular front right where the surface position shows. Earlier in the presentation, I showed you how to figure it out based on a frontal slope that you might be given. So, whether you're in the real airplane flying and you're wondering exactly where you might meet this weather, don't forget about the mixing zones and or the slope. If it's a cold front, you'll hit the weather and then you'll be in it for a while if you're approaching it from the warm side. If it's a warm front and you're approaching it from the cold side, well, you're going to encounter it early and you're going to encounter it for a long period of time. If you are aloft and you are approaching it, you're going from warm to cold. You won't encounter it initially. You'll see it below you, but then you'll encounter it much later on. So you can see there's all sorts of combinations. Make sure you think to the diagrams that I've shown you, though, and then think about, am I at the surface or am I in an airplane? Where will I actually meet this front? Where are the mixing zones? Whew, that was a lot, wasn't it? I'll say, you now know a lot about fronts. And, having said that, I think I'm going to move to the front a little bit here. Until next time, I'll see you later. I'm Aaron for PilotTraining. See you.